hi again. I was told there is popular demand for debloating, so I figured I would present too. Yeah, this is another debloating work, collaboration with Boston University, and I'm immensely thankful for my colleagues Rasoul and Chris for their contribution to this work and insights from Manuel and Nick. Without their help, this wouldn't have been possible. The title of this work is AnimateDead, and in this work, we're trying to debloat web applications via Concolic execution. So a little bit of motivation here. In previous debloating schemes, we relied on dynamic instrumentation, and therefore, this information was costly to collect. There was runtime overhead of running these traces, and an issue is that when you're collecting information from real users' behavior, there is a chance that there's underrepresentation for error-inducing code paths or less popular features. And if you miss them in your debloating, then you'll run into an error. And more importantly, if you dynamically debloat applications with specific state of the database and network, chances are when the database changes or if the network goes down, you have already debloated the code that's supposed to handle those scenarios. So our idea was to build a PHP emulator capable of concolically executing applications and then explore and see which parts are reachable and which are not. So let me dig deeper into the web server logs. We talked about them. They're good because they're collected by default. There's no instrumentation overhead to collecting them. And if we look at these logs, which are for a WordPress website, you can see that the user was requesting the login endpoint. And then you can see another request trying to load the styles. And you can see the get parameters in there as well. But the logs, for a good reason, don't include all pieces of information. For instance, post requests, the parameters by default aren't present in the logs because they can contain sensitive information, such as passwords. Similarly, no one logs file uploads by default because they can take up a lot of space. You don't log cookies. And there's server-side parameters like session variables that are missing from these logs. And then we want to have an analysis that works for all of these unknown parameters and all the states of the database and all states of the network. So our idea here was to mark all of these unknown sources of information as symbolic, populate all the other variables that we know from the web server logs, and then run the application in our emulator. So here I have a simplified code for the login logic of WordPress, and I want to walk you through a concrete execution versus symbolic execution, just to have an idea how this would work. So first, WordPress checks if there is no username provided and shows you an error. Then we query the database to see if the username is valid, and if it is, then all good. If not, we check if there's an @ sign in the username, and if there is, the user may be trying to log in via email, and these are separate columns in the database, so we have to query the database again. And if either of these calls succeed, we would redirect the user to the admin panel, and if they fail, we show an error to the user. So if we dynamically run this code and the user successfully logs in via a username, only these lines are executed. But in reality, if we're doing an analysis, we are interested in all of the branches in this code. So in order to execute these other branches that I mentioned here, we have to look at the parameters that determine whether those conditions are satisfied or not. And in the first example, in the first one, we have a post request username that is provided by the user. It's a symbolic variable in our execution because we don't know what it is. In the second and third one, get user by login and get user by email, we're interacting with the database. So again, we replace the return values with the symbolic variable. And by doing so, we can execute all the branches in this piece of code. So at a high level, we translate the log files of the web server log files to entry points. We do a reachability analysis using concolic execution, and then we remove whatever that's not reached, and that would be our debloated application. So in order to do this analysis, as you saw earlier, we have to execute multiple branches in parallel. So we designed a distributed concolic analysis infrastructure, which starts with an orchestrator that puts a task on the queue. This could be analyze a get request to post.php page with ID equals 2 parameter. Then we have a pool of workers, which are PHP emulators. They pick up this task, start executing the code, and then at some point they may reach a condition that they don't know if it can be satisfied or not. So they'll take one of these branches and put another task on the queue for the other workers to explore the other branches in the code. And we continue doing this analysis For smaller applications and simpler entry points, this would exhaustively explore all the branches in the code. But for more complex applications, you have to define a timeout to stop the execution once you stop identifying new code. And in order to instruct other workers to continue exploring other branches, we defined an emulation replay setup where you can force an emulator to follow specific branches in the code. So imagine we have a piece of code that has 3 branches and we want to explore all of them. The first worker will take the first branch, but then add a new log to the queue saying skip line 1 and explore line 3. The second worker will pick it up, explore the second branch, and put another task on the queue to skip lines 1 and 3 and explore line 5. And therefore, we're able to explore all the symbolically satisfiable branches in this code structure. The gist of AnimateDead is concolic execution, and by that we mean the transition from symbolic variables to concrete ones. And that is vital in specific cases where the code is modifying the structure of the call graph. Similar to minimalist, if you have a file inclusion, if you have a function call that's symbolic, you cannot continue your analysis, and you need concrete candidates for those variables. More specifically, if you have these instructions, include, require, include once, you have to do this translation. Same for instructions that can trigger the autoloader. In PHP, you can just instantiate a new class, and this callback would go ahead and find the definition of the class and include it for you. So you have to have a concrete class name. If you have a dynamic function call, and if you have a callback where the callback is a variable, again, you have to translate that symbolic variable to a concrete variable. And to enable doing so, we perform some analysis. So for example, we need to know the types of these variables. And PHP by default does provide some optional ways of determining and defining types, but not all applications have that. So what we did was we created a mapping between PHP APIs and the return types. So if you have a symbolic variable and you run substring on top of that, we know that the return value has to be of type string. Similarly, if you run isSet on a symbolic variable, you know that the return value is either true or false. In the same way, if you check whether a variable is instance of a class, then within that block, within that condition, you know the type of the variable. Moreover, we need to do a value set analysis. And in this case, we model the string operations to regular expressions. For example, if you check whether the name of a cookie starts with PMA, then you can translate that to a regular expression, PMA.star, and then later on you can check whether that string matches this regular expression or not. We also model set memberships in AnimateDead, which essentially means that if you're checking whether a user-controlled value is within a set of allowed operations, then we know that one of these concrete values is the value of the symbolic variable. And this is a common use case in web applications because for user-controlled variables, for database variables, you need to perform an allow list check to prevent damage. And lastly, we get help from the execution environment. So if you're trying to include a PHP file and you know the prefix and postfix of that, there's only so many PHP files on the file system that would match this pattern, and then we can include each of them one by one and analyze the application. One issue that you would run into doing concolic execution is state space explosion, which essentially means that if you have too many of these symbolic branches back to back, then you have an exponentially growing number of unique paths in the application that you need to explore. And in order to address that, we first eliminated all the unsatisfiable paths to limit the total number of paths we need to explore based on the previous analysis that I showed you. And we then try to prioritize paths based on their likelihood to explore new parts of the code base. One intuition that we got after our analysis was that in PMA, 72% of symbolic conditions only check for presence or absence of a variable. And this is, again, a common practice because web applications check if a post parameter is present, if a cookie is present, and then determine which page to show to the users. And knowing that, we configured our web server to augment the logs and tell us if a post parameter is present or not, if a cookie is present or not. In this case, we don't care about the values. We just want to know if that value was populated by the users or not. On top of that, we experimented with DFS, which essentially means the next path that you identify, go and explore that. versus a more efficient path selection, which we called branch coverage guided path prioritization. And again, the intuition here was that we wanted to make sure we do not get stuck in loops and we maximize unique code coverage. And there's more details to that, but for that, I'll refer you to the paper. After we run the application concolically, we have a bunch of execution that tells us which files and functions were executed. We put them all together, and then we debloat the applications, and now we can look at the security metrics. In terms of size reduction, if you look at phpMyAdmin, for example, AnimateDead reduces the lines of code by 69%, whereas dynamic debloating of less is more reduces this by 77%. And looking at other applications in our data set, you see that the numbers of AnimateDead and less is more are within 10 to 20% of each other. Next, we looked into CVE mappings to the source code of applications for the two applications that had publicly reported CVEs, and we saw that AnimateDead for phpMyAdmin reduces 65% of CVEs compared to 80% of less is more, and the numbers are similar for between AnimateDead and less is more for WordPress. And the takeaway here is that the numbers are comparable to each other, but in one case we're doing static debloating, so we don't have any of that overhead. And another detail is that less is more and AnimateDead are operating based on different inputs. In AnimateDead, you're taking the entry points, so for, let's say, login.php, you're keeping all the code that's reachable from that page, but in less is more, if you only log in successfully, you remove all the other code paths and error handlers in that code. So with that, now we can talk about the conclusion. So we showed that using Concolic execution, we could perform a reachability analysis on PHP applications. We showed that the debloating metrics of AnimateDead are comparable to dynamic debloating schemes, and we have our source code available on debloating.com. So I'm happy to take your questions now.